Hello, and welcome to When Failure is Not an Option. When a cloud platform offers 99.99% uptime, it means that if there are 2 million database instances running in a single cloud center, 200 of them will go down at any given time. Russian roulette may not be one of the features your cloud platform offers, but it's there, and you have to manage it. On the moon, failure was not an option, but in the cloud, it's guaranteed. Today, RavenDB CEO Oren Eini will talk about the most common failures applications encounter on the cloud and how to handle them, or how to rest easy knowing that your RavenDB Cloud managed database is handling them for you. If you have any questions at any time, click the Q&A button at the bottom of your screen, and Oren will be happy to answer them at the end of the presentation. Enjoy, and here's Oren.
Hey, David, can you see my screen?
Yes.
Okay. So the point of this talk, and I really like the title, is that we can't ever assume that a failure is something that we can avoid or prevent or in some manner escape. Failure is something that we're just going to have to deal with. And this talk is all about how we can actually use that, how we can actually work with failures and handle them in a consistent and reliable manner. So the first thing that I want to discuss is what happens if we have a failure that is 1 in a million chance for something to happen. Now, 1 in a million sounds like a very unlikely to happen. Something that, oh, it's a 1 in a million chance, never going to happen. Well, I'm talking to you right now with a machine that has 3 gigahertz base speed and 20 cores. That means roughly that a 1 in a million chance can happen on these machines 60 times per second. And that's utterly ridiculous. David earlier gave you some numbers about what happens if I have 2 million instances and stuff like that. But even if you're talking about ridiculous number of SLAs, in this case, I have 7 nines. 7 nines translate to 3 seconds of downtime per year. And that is an utterly ridiculous number. But the idea here is that even if I promise you 7 nines, if I have 1,000 machines, 1 machine can be down for 52 minutes on a year. If I have 10,000 machines with 7 nines reliability, I can be down for 8 hours. Now, if those are 10,000 interchangeable machines, that's great. But if those are 10,000 machines, each of them doing something unique, I got someone who is going to be stuck holding the dirty end of the stick. So how do we handle and work with that? I actually ran into this yesterday. This is from yesterday, I ran into this today. And this is a great example. You had a power failure and backup doesn't run and EBS died and stuff happened. But if you go and look at the AWS status, you're not going to see a sea of red. You're going to see, few customers were impacted. And AWS has so many customers that it doesn't even touch their SLA. But for that particular person, for Andy Hunt, who is very well known, then that's a killer. Now, let's talk about what is a failure. And for the purpose of this talk, I have 2 types of failure that I want to address. One of them is this guy. You got some of an error, something that's problematic. And that's probably the most obvious example and the best thing to have. The worst sort of failures is this. Something is slow. Especially if this is something that is slow only some of the time. If you're looking at your performance numbers and you're seeing that, oh, my 99% percentile is very high, that means that 1 in 100 requests is slow. Maybe 99.9% is high. 1 in 1,000 requests is slow. And now you need to figure out what's going on. And from experience, those kind of bugs, those kind of issues are the nastiest to try to resolve. So when we set up to design RavenDB, and we did that in 2 stages. In 2008 and 2009, I set out and designed what I thought to be the perfect document database. I have a 12-part series in my blog talking about designing a document database. If you go look at that today, you can see that I have pretty good concepts about how to handle things, what I should look at. At the same time, in 2015, we put a break. We took 5 years of production experience and rebuilt everything from scratch. And we built everything from scratch with actual real-world experience about where does it hurt. So in the real life, you constantly expect failure. And we don't try to prevent it, but we do try to work with it. When I'm driving a car, I put on a seatbelt. My car has airbags. If I'm taking my family rafting, we are going to put a survival vest. I don't expect to be in a car accident, but the cost of not wearing a seatbelt is so high that even for the unlikely scenario, I absolutely want to have that. So the same applies for RavenDB as well. I want to have a seatbelt. I want to have the airbags. Sometimes you have to pay extra for those features. We certainly spent a lot of time and effort implementing them, but the idea that failure is something that you just got to deal with, it's not something that you can say, oh, it's someone else's responsibility, has been one of the core concepts that we put into RavenDB 4.0. So the question here is, what can fail? And the simple answer is that everything can fail. But this simple answer is non-actionable. If everything can fail, if I have to walk around CPU bugs, well, there's not much I can do about that. So I have to trust something. I have to start from some place and then move on. So I trust RavenDB to some amount. And there are typically common causes for most issues. So network and I/O are very common cause for issues. Liveliness in the cluster is a cause of issues. There's a whole bunch of stuff. I'm going to go over them in details. But the basic idea is that whenever we do something that is internal to RavenDB, I trust that. Whenever I have to leave RavenDB, whenever I have to talk to the network, which is obvious, the network is not reliable. It's always going to cause us some issues. But the same is also true when I'm going to talk to the disk. I don't trust the disk. The disk sucks. It's slow. It can give me errors. Someone else can go and modify the data on the disk as I'm writing that. So that's something that I have to be aware of. We used to have a customer that had a big issue. Sometimes RavenDB would corrupt itself. And every week or so, they would run into this issue. And what ended up being the case was that they have an antivirus that installs some sort of a file hook that would sometimes modify the behavior of certain system calls, which RavenDB rely on for reliability. And at that point, I'm saying, okay, I can't trust the operating system. I can't trust the hardware. There's not much I can do about that. But even so, at some point, we actually detected that and alerted on this. But let's see what are the kind of things that I would expect in a normal environment. And the simplest scenario that we have to deal with is the notion of a network outage. Now, what does it mean? Network outage means I can connect to something. As a server, that needs to connect to another server in the cluster, okay, I can connect, I'm going to retry, and that's it. As a client, what do? Now, the idea here is that this is something that we design directly into the way RavenDB, both client and server, think about the world. Whenever RavenDB client connect to a cluster for the first time, the very first action that it does is going to ask, what is the topology of this database? And by topology, I mean, what are the nodes that this database resides on? And you can see it right here. This database resides on A, B, and D. Why is it the first thing that we do? Because without that, I don't know how to get to, I don't know how to deal with what happens if one of the nodes is not responsive. At the simplest level, RavenDB uses something called a multi-master setup. Every node in the database can accept reads or write for this database. What this means for the client is that the client is absolutely capable of saying, oh, you know what? I'm going to try to talk to node A. And if node A is not responsive for anything, it can be a timeout, can be a TCPO, any of those sort of things, the client automatically knows that it can go to node B. And if B is down, it will go to node D. So there's nothing that the other members in the cluster needs to do. The client has already been made aware of what is the policy for handling failures. It gets more interesting because the server side also has some pretty heavy responsibilities with regard to handling failures. A RavenDB cluster is composed of some nodes that all work together for a common goal. Those nodes will select a leader, and one of the primary responsibility of the leader is to watch over the cluster. So when the leader of a cluster notice that one of the nodes is down, it is going to take action. It is going to mark that node as rehab. As in, I don't know what your state is, go to rehab until you prove to me that you are ready to be a useful member of society. In this case, something really interesting happens. Whenever the cluster, whenever the leader of the cluster decides to change the topology of a database, whenever it's, for example, if node is down, then we're going to say, okay, let's take node B and move it to rehab, and that change the topology of the database. The next time a client makes a request to the server, it is going to be notified about the change. And if the client is using the changes API, which usually you would, the server would actively go and tell the clients about this topology change. When this happens, the client will go and get the new topology. What this means is that the moment a new topology happens, it very quickly is being updated on all of the clients. And that gives us a much easier way to handle things because we now have two stages. Stage one, a client observes a failure and completely on its own accord, without needing to go and talk to anyone else, it uses the already defined policy in order to handle how to fail over. The server-side behavior is to observe and detect failures and change the topology accordingly, and then notify all of the clients. So effectively, you can think about this in two ways of actions. Now, outage, I mentioned, is the absolutely simplest scenario. There are more complex scenarios. Let's look at this one, a network partition. Now, there is a lot going on in this slide, so let's take it one step at a time. In the top of the slide, you can see a 3-node cluster when one of the nodes is down. On the bottom of the slide, you can see the same 3-node cluster, but now we have a different behavior. Now the node is up, but it is partitioned from the other members in the cluster. It is important to understand from the point of view of the other members in the cluster, they can tell what state is true. They don't know if that node is down or unreachable. Now, the complex part here is that the client may talk to the isolated server. At this point, a few things happens. You get to choose whatever you want to have your transaction run in a multi-master mode. That's, in this case, what would likely happen is that you will read or write from the isolated server, which is fine. Once the partition is healed, all of the data will sync up properly. Alternatively, you can use a cluster-wide transaction. And a cluster-wide transaction would require you to go only to the majority side of the cluster. If you go to the isolated one, you will fail, and then you will fail over to one of the other ones in order to make this work. There is also another thing that is important. There is a topology change event that happens. What will typically happen in such a scenario, the cluster will detect that this node has been partitioned. It doesn't know that it is down or not. It's concerned, it's unavailable. It will move the isolated node to the rehab mode and notify the clients, hey, you need to talk to one of the other two. This way, again, we have this propagation of data and propagation of state that happen automatically. The whole thing was designed very explicitly in order to ensure that that either option would be sufficient to cover the common cases, and both of them together give us quite a lot of power and flexibility. If there is an issue, we typically don't care. And when we run our own systems, we typically do rolling updates. Rolling update basically means, okay, let's shut down one of the nodes, update it, bring it up again, move on to the next one, etc., etc. We actually, we needed to wait for the node that we just updated to start up again. We had a bug. We didn't do that. And we only caught that 3 months after we started doing these rolling updates. And this is something that we had a script that every night we'd install the nightly and test it and test it and test it. And we never noticed that because of the multi-master nature of RavenDB. Oh, at some point we got to the point where one node was down because we just started it, and we started shutting down the next node. We had only one node in the cluster. We did not notice, and that was the test environment that we were hammering while we were doing that. Okay, now let's talk about recovery. Once something happened, we handled that. We moved node G to rehab. What happens then? What happens when connection is resumed? What's going to happen is that the cluster is going to assign a mentor to this node. That mentor is going to push all of the changes that happen in the database that this node has missed, and it's going to continue pushing everything until that node is synced with the rest of the cluster. It's also going to, the cluster is also going to wait until that node has caught up with all of its indexing, with all of its backlog of work, basically. And then it's going to promote the node from rehab mode to active node as usual. This is, again, this is the topology change. A topology change means that clients are aware of that. Now, a client in rehab mode is still part of the database scope. It's still part of the nodes that compose the database. Why is that? By default, clients will really try never to talk to a node in rehab. But if all of the nodes in the database are in rehab mode, or if there is a node in rehab mode and another node that is active but I can't talk to, I would still go and talk to the rehab node as a act of last resort before I just throw my hands up and throw an exception to the user. Errors are easy. Performance is hard. If you have something that is slow, that can be really nasty. Again, debugging performance issues is the worst. Now, if you're talking about production systems, we have to deal with stuff that changes that may be beyond our control. A recent case that we ran into was that a user was running RavenDB on a burstable instance on a cloud platform. This burstable instance starts from, oh, you can do network transfer at the rate of 625 megabytes, not that this is megabytes, not megabits, per second, but you only get some of that. Once you consume all of this bandwidth, you start being throttled, and the throttle is ridiculous. Less than 4 megabytes per second. Now, just to give you some numbers, if you have a lot of data to transfer, you can churn through the burstable performance within less than a minute. At that point, you're now moving, oh, I used to send hundreds of megabytes per second, now I'm sending 4, 3, whatever. Utterly ridiculous. Now, think about this from the point of view of the admin that needs to look at something. Hey, why am I not seeing updates propagate properly in this environment? And in order to handle that, we actively monitor a lot of what's going on, and we expose that to you directly. If you go to the database page, you can see that in the status, you have ongoing task stats. This is what RavenDB monitor interaction between servers. And you can see there is a nice timeline view, and you can see exactly what's going on. I sent 3 documents, it took you 24 milliseconds, everyone is happy. Or you will see, okay, I sent 1,000 documents, the total amount of space that it took was 3 megabytes, and it took me 3 minutes. And at that point, there are certain things that RavenDB can't help you with. We can't get more bandwidth from the infrastructure. What we can do is expose those details to you so you can then go and maybe get a better machine, maybe go and change the network cable. Other issues that we run into is, for example, if you have a host name that has both IPv4 and IPv6, but your server is only bound to IPv4, the typical behavior of with TCP is that you first try to connect to the IPv6 endpoint, but you're not listening to that. At this point, it's going to connect until it times out. Typically takes a second or two, and only then will it try to go and talk to the IPv4. That means that you have a very long connection time. Other example may be because RavenDB is using a TLS, HTTPS, SSL, whatever you want to call it, for encrypting the data in transit, then we need to do SSL negotiation. That can take non-trivial amount of time in certain cases. So we have to deal with connections that establishing a connection between servers or between a client and a server may take a very long time. We deal with that by using connection pooling. Connection pooling allows us to reuse a connection. That means that we have to have internal protocols that allow us to reuse a connection. Luckily, not a very big issue. But the primary problem with connection pooling is that you have to deal with poisoned connection. I put a connection in the connection pool. That was perfectly fine. Now I pull it out, and between the time I put it in and put it out, it has been poisoned. Something caused to break this connection. There was a timeout. The network appliance decided to drop this connection, whatever. Now trying to connect to this, and it's always going to fail. So we have ways of dealing with that and how to handle this, and this is a significantly complicated topic. A really great example of how this can happen is what happens if I have a connection that is point to IP 10.0.0.2, and the server moved to 10.0.0.3. But I have a connection ready for 2, and that connection is still open. It's just never responding to me. So that's fun to have to deal with, but we deal with that. The network is unreliable, and that's probably something that you already knew. But the network is really, really unreliable. We had a case where we were trying to run performance monitoring on a system, and the results were atrocious. And then we realized that there was a literally bad cable. We changed the cable and everything went up. I had another case where a customer was actually using Wi-Fi. They were running RavenDB as a Windows application inside of a desktop application, inside of laptops connecting to Wi-Fi, and we suffer from the packet drop because of this issue. And that could also cause, packet drop can cause high latency of the connection. It can cause disconnection of TCP. So we have retries, but retries are not enough. I try to connect to you, I fail. Try to connect to you, I fail. It doesn't work. We have exponential backoff strategy there up to some limit. We know how to adjust the size of the buffers that we're trying to send off the network to increase the chance that even on an unreliable network, I will still be able to make some progress. Something really nasty that I don't know if this is something that is widely known, but network appliances sucks. I mean, they just suck so bad because they basically mess up with everything that's going on. But one of the nastiest way they can do things is to just drop packets for no reason. For example, you have a connection between a client and a server. That connection goes to network appliance A. Then it goes to network appliance B. Network appliance B has a rule that says, oh, after 30 seconds of inactivity, no packets going on in a particular connection, I'm going to just drop this connection. And then I'm going to silently drop every additional packet that I'm going to get for this connection. From my perspective, everything is perfect, but I'm never going to get another packet on this. And that means that the TCP buffer on my end is going to get full. And in some cases, depending on load and the system configuration of a TCP buffer, that can take minutes until that issue is going to result with an error code in my end. The way that we handle that is that all of our internal protocols will always send pings over the TCP connection. So we have specific data frames that we can send that the other side not to ignore, whose only purpose is that, oh, I have nothing to send you. I'm alive, I'm alive, I'm alive. Make sure that the connection is alive. It sounds silly, but it had a marked improvement in the reliability of connections in some cases. Funny enough, mostly for development. Try to imagine, oh, as a developer, you're working on a system and you go to lunch, you got a call, something like that, which is exactly the case where, oh, there is a connection that's already established. It goes to some of your corporate network infrastructure, and then it just goes away. And now you have a real world bug where it says that RavenDB fails to connect every time I go get a coffee. And now we are like, RavenDB doesn't discriminate against coffee drinkers. Coffee drinkers are fine. Tea drinkers, we need to talk about that. Other issues that we have with networks and bad networks are with laptops, especially laptops that come and go in various locations. Some of the issues there is that sometimes you work from Starbucks, sometimes you work from home, sometimes from the office, but you need to have some way of connecting to the rest of the world. We have pull replication that allows you to have the instance that is running on that particular location, on that laptop, for example, and that would go out and connect to the well-known instance. This is also used very frequently in the shipping industry. If you have RavenDB running inside a truck or inside a ocean ship, then every time that you actually connect is in a different location. And in many cases, this is a bad network location. Pull replication helps, and then pull replication builds on top of all of those features in order to create a highly reliable system. This something that can make forward progress. That's actually really important. We don't necessarily need to be perfect. It's okay to get errors, but we need to make progress over time, especially under harsh conditions. Okay, now, we don't trust the network. If you're running on a hotel network and you're trying to connect to somewhere, someone is listening to that. If you're running on a corporate network, there is someone listening to the network. Maybe it's the red team in your company, but we got to assume that this is the case. So RavenDB had a formal security review about how we do things. All of our data is encrypted over the wire using TLS 1.2. And whenever two nodes talk to each other, and two nodes can be two servers or a client and a server, they're going to mutually authenticate one another. Now, one of the primary issues that we have with security is that in many, many cases, security also means obscurity. We actually spend quite a lot of time making sure that when you get errors because of security, you will get good errors. You get errors that tell you, oh, you tried to access this database, but you didn't use a client certificate. Or you use a client certificate, but it's not one that I know. Or you use one that I know, but you don't have access to this guy. Stuff like that. The security model for RavenDB has been designed explicitly to also be debuggable. In addition to the errors that we give you, it means that you can inspect the state of the system only with local state. For example, let's assume that I'm using Windows Authentication. If I'm using Windows Authentication, an authentication request may go from my machine to the domain controller. If I'm using a forest, it may go to a different domain controller. There are all sorts of security levels all along the way that might interrupt what I'm doing. And it all gets really, really complicated, especially because the DBA that is managing RavenDB is not necessarily the guy who is doing Windows administration. So having a security system, an authentication system that is completely and utterly locally debuggable is huge for that. In many cases, I can just ask RavenDB, what's the issue? And it is able to tell me. And that can save us quite a lot of time, and effort. If, I can see that the certificate has expired, I don't need to go hunt stuff. I can just figure it out. Something really important, we use the non-Byzantine model. Basically, it means that we don't assume that the other sides are hostile. If you connect to RavenDB after you authenticated, we are going to assume that you're doing things properly. We are still going to validate the data. We're still going to ensure that what you're saying makes sense. But if I have an authenticated connection that comes and says, oh, here are some documents, I'm going to accept those documents. I'm not going to try to, prove me in some manner that you are viable for me to, those documents have been appropriately validated or something like that. That's not something that we do. Now, let's talk about I/O. I/O is a really annoying subject for a database because For many of the high-end operations, lots of writes, lots of reads, stuff like that, I/O is king. And the problem here is that I/O can really mess you up. I mentioned earlier that we had some issues with burstable performance of network. Well, let's talk AWS as a good example. A GP2 drive has a burstable capacity of 3,000 IOPS. You can burn through that under load very, very quickly. And then you get to 100, 200 IOPS, which is effectively nothing. In order to handle that, RavenDB actively monitor I/O. And if you go below a certain threshold, we will pop up an error to the alert to the admin. Tell, hey, something is wrong. And the idea here is that point the admin can go and fix something. I had a case where people run RavenDB on a high-end SAN, but they set up the quality of service setting in such a way that RavenDB was starved out of I/O. And this specific error, this specific alert was the smoking gun that we needed to say, oh, this is the case. Now, in addition to the smoking gun, you actually get full tracing of all of the I/O operations that RavenDB is making. For example, here's a journal write of 204 kilobyte. It took 1 millisecond, and you can see that's awesome. That's awesome performance to have. But just being able to see that, and there is a nice timeline view, so you can see all of the writes over times and be able to say, oh, I can see that I'm doing a lot of indexing here. I can see I do a lot of writes here. That means that's why I'm choking my I/O. And that gives you a lot of insight into what exactly is going on in the system. I mentioned earlier that I don't trust the disk. I don't trust the disk because it's mutable. I'm writing stuff to the disk, and then someone else can mutate the data. Now, there are two ways in which we protect ourselves from that. The simple way is that we use a XXHash to validate that what we wrote and what we read from the journal is the same. So that's primarily because we're going to say, oh, we wrote some data to disk, and we aren't sure if that transaction has completely reached the disk or not. If it didn't reach the disk, then if it reached the disk but not everything was written properly, then the hash would be different. We know that we had an issue, probably a partially written transaction, which is fine. We just roll it back and everything is good. This also helps us if someone goes and tries to modify the disk, or if someone, for example, if we have a bad sector in the disk and we get bad data. But that's for journals. When we talk about the data, whenever I read a page from this for the first time, I'm going to validate its hash. I read it from the disk, validate the hash, now I can move on and deal with things. Next time I'm going to read this page, well, I already validated that, I'm okay with this. If I'm using encrypted databases, I'm actually taking this a few steps further. On every access to the disk, to the journal, to everything, I'm going to revalidate the data. Now, so good. I'm taking specific actions against the errors and corruption. There are a few things that I can't deal with. What do I mean by that? For example, it's very important for RavenDB that when I'm writing data to disk and I'm telling the disk, make sure that this is persistent, that is what will actually happen. There are certain hard drives that just don't do that. You tell them, make sure this is persistent, and they will write them to volatile memory inside the hard disk and say, yes, that's okay, we're persistent. And if you have a power outage, you have data corruption because the driver lies to us. We're also seeing related issues around a file system. For example, CIFS when running remote There are certain operations that it doesn't support. Doing an fsync on a directory, which under some circumstances may require us to handle things properly. If it doesn't work, it doesn't work. There is literally nothing I can do about that because the system just doesn't want to behave. We are actually handling a lot of cases like that. We're saying, okay, if you're running a CIF system, we are not going to do an fsync on a directory. That exposes to some strange edge conditions if the server running the CIF system died. But unfortunately, this is common enough that we just have to deal with that and document this as a limitation. Now, let's talk about memory. It's problematic because memory is a finite resource, especially because now we have users who are running us in containers with very limited amount of memory. We have users who are running that on VMs, the tiniest VM that you could possibly imagine, stuff like that. So we need to be very efficient in our memory usage. Even more than that, RavenDB is written using .NET Core. .NET Core is a managed language, and it is using a garbage collection. One of the problems of a garbage collection is something called GC pauses, when the GC needs to collect garbage, and it needs to stop the world so it will have the chance of collecting all of the generated garbage. That can be quite expensive. We have set RavenDB to have these settings, retain virtual memory. So even if we're not currently using memory right now, don't release the memory to the operating system. Make sure that we keep it so we can use it soon. The idea here is that we don't want to have a ping pong of allocate memory from the operating system, release it to the operating system, etc., etc. The other options are for concurrent garbage collection and having a heap per thread or per core. And basically all of them increase the performance of the system. That's good. That's settings that you might want to consider for your application as well. For RavenDB, it wasn't sufficient. What we did, we started moving a lot of data directly into native memory, where RavenDB is the one who is responsible for the data management. RavenDB is the one who is doing allocations and tracking and optimizations like that. This ended up being really important because it allows us to tailor the memory access and memory allocation strategy toward what we want to do. Even more important than that, it also means that we don't have to push so much memory into the GC. Most of the memory that RavenDB is using in the normal case is native memory, which means that the GC has a lot less work to do. That means that we have far fewer GC pauses, and they tend to be they don't tend to be something that you actually pay attention to. Now, RavenDB allows it to run itself in 32 bits. 32 bits typically means that you have access to a 2 gigabyte virtual address space. And 2 gigabyte, I remember 2 gigabyte being an insane amount of disk space. Disk space, remember, not memory, because who can afford that much memory? Memory was, oh, I have 16 megabytes of memory. That's amazing. That's, you know, let's break the savings account for that. But with 32 bits, 2 gigabyte today is almost nothing. You have to work very, very hard in order to deal with that. And one of the primary problems that we have is the issue of address space fragmentation. If you keep allocating and deallocating different sizes, you may break the virtual address space in such a case that when you need an allocation of a certain size, there is no virtual address space big enough for you to handle that. And this is without even taking into account the fact that you might actually have enough physical memory available, but no place to actually create a continuous array of this size. So we deal with that, again, with manual memory management, with making sure that all of our locations are in a predictable and reasonably sized amounts. When we're using 32 bits, we are not using return virtual memory because we do want to release the memory as soon as possible. So if there are sparks, they would be released back to the operating system as soon as possible, and all much of other stuff like that. Memory is a finite resource. So there are certain servers that have terabytes of memory, but RavenDB tends to run on machines that range from 512 megabyte to a few hundreds of gigabyte. That means that we really have to take care of efficiency. And efficiency actually goes both ways. So if I'm running on a 512 megabyte system, I really care about all of the memory that I'm using. And I want to use as little as possible because I don't have a lot of space to work with. On the other hand, if I'm running on a system that has 256 gigabyte of memory, I absolutely want to use as much of that as possible. Otherwise, I have a user who just purchased a lot of memory and I'm sitting there using nothing. RavenDB memory usage is divided into three categories. There is the native memory, where we are doing most of the work. Accepting the request from the client, parsing that, all of that is done using native memory. A lot of the ongoing work is done using managed memory. So if I want to have a dictionary, I'm just going to use the .NET dictionary and not try to implement my own using native memory. If I went that way, I might as well go and write the software in C. But there are a lot of benefits of actually being able to utilize a lot of the features of a managed system. In a typical environment, the biggest usage of managed memory in RavenDB would be indexing. If you don't have indexing, typically the amount of managed memory you see is relatively low. Most of the data in RavenDB is actually memory map data. Data that is sitting on disk and has been mapped to memory to be able to work with it directly. In order to allow us to do that, we're using zero-copy data structures, which means that in most cases, I can effectively give you a pointer to a location in disk and just send it over the network, and that's it. Something that is really interesting is that we don't do caching, at least not explicit caching. One of the problems with caching is that it gets really hard to manage, and in many cases, it's easier to get into situations where the cache itself is the problem. So RavenDB doesn't try to do caching. Instead, it relies on the page cache of the OS. If we access a particular page, the OS is going to make sure that it's in memory. It's going to keep it in memory for a while as long as we are accessing that. Because we use zero-copy data, it means that we don't need to do work to access or work with the data as we are dealing with that. So we don't need a separate cache. We can just use what the OS is giving us. And OS tend to have better overall insight over what's going on in the system. Network I/O, memory, and now we're talking about CPU. You might notice that those are all of the things that makes up a computer. As I mentioned, everything that is not RavenDB suspect. Now, CPU is also a finite resource, and it's finite resource in an interesting way. In a cluster, I need to ensure liveliness. I need to ensure that I'm running through I'm able to communicate with all of the other members in Node in a timely fashion. I'm able to answer requests. I need to index. There are background operations that I need to do. And the way that we're doing that, we created a set of tiers. What is important, what is less so, and what can be done at some point. And we're using thread priorities in order to tell the operating system how do you want that to happen. And the idea here is that for example, making sure that the cluster is alive is kind of important. So let's give it a high priority. Processing request, I have a user sitting waiting on that. The backup process, I don't care if it takes more time. So the idea here is that we prevent bottlenecks. A good example here, let's say that I'm going to create a new index. That index is going to be created with a lower priority. It's going to be bound to a particular core, and then it's going to just sit there and run and run and run and churn through the data. This may mean that the indexing process for the new index will take a little bit longer, but it also means that introducing a new index is not a scary event. It's just, okay, it will happen. We are also going to make sure that RavenDB is going to have at least one core free from all of these background operations that we can use to run operations. By the way, general recommendation, if you run in RavenDB on a single core machine, there is no additional core that we can create that would give us some spare capacity for doing things like cluster, request, stuff like that. So try to run RavenDB always with at least two cores. At least the primary issue is that if you're trying to do a lot of work and have a single core, that's not going to be so good. Typically, you're running on a single core only when you're running on the cloud or on a VM. If you're a VM, typically you can just ask for two cores, that's not an issue. In the cloud, there are certain very low-end instances, very low-end instances that only have a single core. And if that's the case, consider upgrading if you see that you're stressing the system. Speaking of low-end instances in the cloud, it's common in the cloud to run using something called burstable instances. Burstable instances have a set amount of CPU credits, and once they burn through the CPU credits, the CPU itself starts getting throttled. Now, this is nasty thing to handle, because from the point of view of the outside world, this behaves just like a GC pause. The system just goes away for a while. And it's hard to debug because, I'm trying to SSH into the machine, but there is no spare capacity for me to actually be able to do that. A whole bunch of stuff like that. RavenDB is actually, you can configure RavenDB to say, I'm running on a burstable instance, and then it would start monitoring its own CPU utilization. And it's going to monitor how much CPU credits it has available. Once you go below a one second. Once you go below a certain value, then we're going to start saying, panic mode. We're going to run out of CPU. And we're going to start abort operations. We're going to stop indexing. We're going to stop background operations that we can in order to provide us with some breathing room until you're actually able to process things normally. If it gets really bad, we may start shutting down access to databases, because ideally, I want to get to the point where I'm very quickly giving an error. Hey, you run out of CPU credits. I'm refusing this request, because it's better than, okay, let me try to process this request. That's really, really annoying and really, really hard to debug. There's also another feature here that is very important. When I'm telling you that, hey, I can't process this request, I'm becoming unavailable. Remember what I told you earlier about network outage? This is the exact same behavior. The cluster also monitor the CPU credits that you have available. And if you run too low, it will shift the topology to someone that has CPU credits available. The clients, when it detects that, it has been rejected because of CPU credits, is going to automatically and transparently fail over to another node that has CPU credits. We have users who are actually running at a higher capacity than their CPU credits allow. But what actually ends up happening is that they run on a node and effectively drain off their CPU credits, and then they transparently move to another node, do the same there, and then to the third node, do the same there, and then go back. So effectively, when you look at that in the graph, it's really, really funny. You see three lines that keep going up and down, up and up and up and down. And for their purposes, it's enough. They don't need anything more, even though if they're running on a single instance, that would kill them. Okay. RavenDB also have a few active behaviors against entropy, against failure. The easiest one to explain is the notion of highly available tasks. You can see it here. We have external replication right here, and you have node E. If node E is down, the cluster is going to move the responsibility of this task from node E to one of the other nodes. Now, there are two things here. If node E is still up, certain operation would fail. Something like external replication, we probably don't want it to happen on multiple nodes concurrently. That's not too big of a deal because RavenDB is multi-master and we just handle that. But there are other operations that might be more interesting. For example, backups. Remember that from the point of view of RavenDB, a node being inaccessible may mean that the node is down or the node is partitioned. For backup specifically, we allow it to run on both nodes concurrently. So node E and node B would run the backup at the same time. The idea here is that in the worst case scenario, we have a duplicate backup, no biggie. The alternative is that we may have no backup, which is a big issue. There is also something called dynamic database distribution. When you create a RavenDB database, you're going to create it with a replication factor. This replication factor says what is the number of copies that you need for the data. If a node is down, the cluster starts a timer basically and says, okay, this database now have only 2 copies of the data, but it needs 3. If enough time goes by, and the default is something like 15 minutes, basically enough time for you to restart if something happened, the cluster is going to say, okay, I need more copies of this data, and it's going to go ahead and shift the data around. Again, remember, shift the topology of the database and create another node. That node is going to be assigned a mentor, and that mentor will start pushing all of the data back to the new node. Once we are done with that, then we have the appropriate number of copies on the cluster. When the old node joins up again, we says, okay, now you're no longer relevant for us. We have enough copy. The data that you have is no longer relevant. Let's remove it from this node. And now we have capacity on this node for other stuff that may happen. About the dynamic database distribution, remember again how it works. We have database topology, and the clusters can decide to change the database topology, and the clients are fine with that. They expect that it happen on a routine basis. Now, let's talk what happens when a machine goes bye-bye. Let's say that I have a machine and someone went ahead and torched it. Maybe I was running some cryptocurrency and I didn't pay attention and the CPU went on fire. The hard disk died and now I have nothing that I can do about this. The way to recover from that is very simple. Get a new machine, take the same RavenDB config as you used to have there. If you don't have that, go to another one of the members in the cluster and just copy that and change the URL for this machine and start it up. Now, what's going to happen at this point? You have a blank RavenDB instance that is running where a productive member of the cluster used to be. The cluster is going to detect that and it's going to say, let me send you everything that I have. And it's going to start populating that instance with all of the data that it is supposed to have. Now, it may take a while, especially on big systems, but the overall idea is that once this is done, it's done. You have restored the system. to its appropriate capacity. If there are other ways that you can deal with that, you can copy the data to restore most of stuff like that, but those are complex. They may take a little less time, but also complex. This is just startup, wait, it will fix itself. One of the fellow modes that we have to consider is users, which is funny because user error, let's call it this way. For example, I ran a query and I didn't notice what I was doing. Or we deploy a new version to production and there was a bug. I accidentally deleted the document or collection or database, basically an oopsie. Now, RavenDB has a few ways of dealing with that. You get to do external replication. An external replication is something that allows you to copy data to basically have the same replication as usual to some other database, maybe on the same cluster, maybe in a remote location, DR environment, whatever. But the idea here is that instead of pushing the data immediately, we're going to push that on a delay. So you have an environment that is 6 hours behind your production one. If something bad happened there, you can cut the connection and switch over to the environment, and that is the live system. You don't have to start dealing with, oh, how do I recover all of that? The other option that you have is revert revisions. Revert revisions assumes that you have configured RavenDB to use revisions, which create an audit log on your system. And then what you can do, you can say, okay, I had an oopsie. Let's go back in time. And RavenDB will use the revisions information in the system in order to roll back the clock to a particular point in time in the system. And that gives you an amazing capability for recovery from certain issues, especially because the revert revision doesn't delete the data. You still have all of those revisions, and you can start applying them one at a time. Oh, I want this one, or this one, etc. But you have the backout button as necessary. There's also additional features that we built, specifically for worst-case scenarios. If you have a single node and the hard disk broke and almost stuff like that, you have a RavenDB database that is that has a bad sector, whatever. There is a tool called Vuln Recovery. You can point it into a RavenDB instance. It assumes that the data is hostile, which basically means that it does a lot of verification. It doesn't attempt to make sense of the data. It basically crawl through your database and compose the system through that. The details are not really relevant, but what is important is that it gives you an output of gzip JSON file that you can then import into another RavenDB instance or just process yourself directly. Two things that we don't check for. I already mentioned that disks that lie to us and hardware that cheat are not something that we can deal with. Get good hardware. It's actually interesting because, for example, if you may get memory errors. I put 1 into this location and I got 62 back. Why? Because the memory sucks. In this case, get ECC RAM, something with error correction, and typically any production system will already have that. If you run in production without this, please don't. There was a famous case for Hadoop a few years ago where they had a single client that had a bad memory, a bad RAM stick, and it kept sending to Hadoop, oh, send me corrupted data, send me corrupted data, and Hadoop responded by effectively deleting all of the data in the database. Cosmic Rays is a thing. Hopefully you may get some superpowers out of that. To deal with that, get a Faraday cage. Nothing I can do with that. Overclocking, overheating, CPU bugs, all sorts of stuff like that. At some point, we're trying to see how fast we can run on a Raspberry Pi. Obviously, overclocking that came up, and we tried that. And if you overclock the Raspberry Pi, interesting things happen when it overheats. Impossible bugs, basically. I'm not dealing with that. In order to deal with CPU bugs, I have to run on the CPU to detect that, and I'm basically in recursion mode there, and nothing to be done about this. The BOS had a wonderful syscall, which is called "Is Computer on Fire?" It was defined as follows. If the computer is not on fire, return 0. If the computer is on fire, the result is undefined. And that's my usual response here. And now, after so much failure and edge cases, stuff like that, here is a picture of a puppy. And if you have any questions, please put them in the Q&A box. I hope that you had a good time listening to this. A lot of that came from bitter production experience and trying to get to the point where we have users that don't need to have a PhD in failure science just to understand what's going on. Okay, we have someone with Cyrillic name that I'm not going to even try, asking, can Raven guarantee optimistic concurrency in case of all failures? And the answer is yes and no. Optimistic concurrency in RavenDB tends to happen on a single node only. And the idea here is that, again, this comes back to the multi-master nature of RavenDB. I'm writing a document to RavenDB with a particular change vector. And if that change vector is a match on this particular node, that would be accepted. It is possible for you to have two different writes to these different nodes at the same time with the same change vector, and that will go true. Why is that? Because of this. I have one write going here and one write going here, both of them with the same change vector. What's going to happen is that this is going to check the local value. This is going to check the local value. It's going to match, and that's going to work. Now, what's the issue here? If we don't do that, we don't get multi-master. We have to go all the time across the entire cluster. Now, we actually have this feature. We have cluster-wide transactions. A cluster-wide transaction is specifically for this case. I want to have an optimistic concurrency or some sort of stuff like that, that is guaranteed to happen across the entire cluster. If there is a failure mode, if I'm trying to write here with optimistic concurrency and a cluster-wide transaction, and be aware that optimistic concurrency with cluster-wide transaction is slightly different, you have to use the compare exchange values, then it would fail. If I go here, I have a majority, I have 2 out of the 3 nodes, it would work. So the answer is that yes, you can do that, and but you have to use cluster-wide transactions. The follow-up to that is how much performance will I lose in case of cluster-wide transactions? And let's talk about the cost of that. A cluster-wide transactions require me to do at minimum. I wrote here. Now I have to write to my disk, send it to this guy, write to this disk, get back, do the actual operation, and then reply to you. So there is an extra 2 writes to disk and 1 network round trip at the minimum for 3-level clusters. I can tell you that we have tested cluster-wide transactions on a typical network, and we could do, I don't remember, it was 2,000 per second, 5,000 per second, big enough that you typically don't care about that. To be fair, if you're running on a single server, you can do 100,000, 150,000 writes per second. But the typical example that I like to give for cluster-wide transactions is the lottery. You have, when I buy a lottery ticket, I want to just accept the right. I bought, this guy just bought a lottery ticket, it went here, remember this here. I always want to remember that, because the alternative is that, oh, I will fail here, and then maybe I will fail in all of them. I had a chance to succeed in recording the purchase of a lottery ticket, I'm going to do that. On the other hand, when I win a lottery, when I want to record who won the lottery ticket, I absolutely never want to have two people win the same lottery ticket. So I'm going to use a cluster-wide transaction in order to ensure that. It's slightly more expensive, but it prevents me from concurrency and consistency issues. And for that particular reason, I want to understand that. Another follow-up, do I have to understand the compare exchange in case I use cluster-wide transactions? To a certain extent, yes. I'm not going to go into more details here. The documentation, I think, does a pretty good job of explaining what's going on. And beyond that, we can, if you have questions, you can go to the support group and ask there, and we would answer that. Do you have any additional questions, any other things that you would like to know? And in the meantime, here is a puppy. Okay, I think this is it. Thank you very much. If you have any follow-up, stuff like that, please let us know. Thank you and goodbye.